All right. Hello, hello, hello. Okay, in this video, we're going to be going over topic 4.2, which is bond types. We're going to talk about four different kinds of bonds. Two of them are real bonds, and two of them are technically bonds. We'll talk about what we mean here in a bit. But for starters, we're going to start with metallic bonds. So I'm going to step out the way so you guys can pause this, write this down, and then I'll go through and give you some information on this. So, yeah. And, okay, I'm going to assume you've done that. Now, metallic bonds are the first fake bond that we're going to talk about. Okay, so metallic bonds are when you take two metals and mix them together. But I want to make a clarification here. When we talk about metallic bonds or alloys, you need to know that. Alloys, that's things that are metallic bonds. We're talking about where we have exclusively metals mixed. Now, this is not a 100% true statement because there are some alloys that have carbon in them. But mostly when we talk about alloys, we're talking about things that are exclusively metals. There are no non-metals present in them at all. Okay, so a metallic bond is going to be a bond between metals. Now, the reason this is not really a bond is because there's no actual physical connection between the atoms. Okay, imagine taking a bag full of blue marbles and a bag full of red marbles and dumping them into the same bucket and then shaking the bucket up. Okay, when you're done, when you look down in it, you're going to have red marbles and blue marbles that are all mixed together. Okay, that's what we're talking about when we say an alloy. They're not actually connected at all. There's no link. There's no working together happening here. There is no actual bond. But they behave differently because of how metals interact with each other. Okay, they don't form a bond, but they do share their properties a little bit. For example, the most common bond, probably that you guys are familiar with, actually the most common is probably steel, but the other one that you probably hear about a lot in history classes is bronze. Okay, bronze was a mix of copper and tin. Copper was, well, pretty common, but it's also really soft. And so it was easy to work, but it was also easy to damage or destroy. Then you have tin, which is extremely strong, but also extremely brittle. It's also kind of rare. And so both of them separately were not terribly useful. But what people found back when was that if they mixed a little bit of tin in with the copper, then the copper became much stronger and it held up much better because some of those properties of the tin were kind of blended together with the properties of the copper. And that made bronze a much more useful alloy, and it was able to hold an edge. Suddenly, these kingdoms that were relying on stone weapons or didn't have really good weapons, bronze was a huge difference because now suddenly they can make powerful weapons or stronger weapons than their allies. Or not their allies. You don't attack your allies. Than their enemies. And if you reheat an alloy, this is another sign. If you reheat an alloy or a compound made up of metallic bonds, you can actually re-separate those metals back out fairly easily. I'm not going to say like it's something you can do in your garage, but it is relatively easy to separate those back out. So yeah, that's pretty much it for metallic. I'm going to scroll down to hydrogen and let you guys write those. All right, once again, pause this, get this written down. All right, I'm going to assume you've done that. Now, hydrogen bonds are also not real bonds, but they are kinda real bonds. There is an actual attractive force that exists that we call hydrogen bonds. Now, this has to do with something called electronegativity. Okay, electronegativity is the tendency of different elements to gather electrons or pull electrons to them. Oxygen, for example, has a very, very high electronegativity. Hydrogen, on the other hand, has a very, very low electronegativity. So what this means is, in a compound or in a bond, electrons will kind of shift away from hydrogen and towards oxygen. And so hydrogens will end up as kind of these positive poles within compounds, which we'll talk more about later. And oxygens and other nonmetals will wind up acting as these negative poles. Well, these positive and negative poles will be attracted to each other. More specifically, hydrogen atoms will be magnetically attracted, electrostatically attracted, probably more accurate, to the lone pairs in oxygens, or in nitrogen or phosphorus or other atoms. But that's what these hydrogen bonds are. They are bonds between hydrogen atoms and lone pairs. Now, where this becomes really important is in proteins. So, freshmen who haven't had biology yet, proteins are these really, really, really big molecules. Okay, and they have to be shaped just right, or they don't work right. Okay, things like enzymes or catalysts, stuff like that. There's others, but that's where this really, really becomes important for. So these hydrogen bonds will form when the lone pair, and by the way, when I say large, I mean millions and millions of atoms large, like really, really, really big. Okay, these molecules, if they're not folded up just right, they don't work. Well, hydrogen bonds will help keep them folded in the right shape so that they can fulfill their function. Okay, they form between the lone pairs on one side of a fold and the hydrogen atoms on the other side of the fold. And there are lots and lots of hydrogen atoms in proteins. There are also lots of nitrogen atoms. So there's plenty of lone pairs to go around. Is there anything I'm forgetting here? Oh, they're very, very weak. It's the fact that there are so many of them that makes them very powerful. But each individually, these are very, very weak forces that are holding these together. Yeah, that's pretty much it. So now I'm going to pull up some real bonds. Let's talk about... All right, come on, scroll to the side. Scroll to the side. There we go. Let's talk about ionic bonds. Once again, I'm going to step aside so you can write this stuff down. All right. I should have done covalent bonds first. Okay, ionic bonds we will come back to. So skip a little bit. We're going to write down covalent stuff first, and then we'll do ionic, because, we need to do covalent first. My bad. Okay, so write this stuff down. Okay, now, covalent bonds are bonds that form between nonmetals. Now, co and valent, this name is there for a reason. Okay, co as in cooperate, valent as in valence or valency. So in a covalent molecule or a covalent bond, electrons are being shared. Atoms are working together to fulfill the octet rule that each of the atoms needs. Okay, so for example, I'm going to put something up. I'm going to use water, because water is a really easy example. I'm going to draw what's called a simplified Bohr diagram. It's kind of a cross between a Bohr diagram and a Lewis structure. Okay, so we're going to start with an oxygen atom. Okay, and I'm going to use red, actually. So oxygen has 6 valence electrons. It has 2 lone pairs and 2 unbonded pairs. Now I'm putting the X in here to make sure you can tell that this is oxygen. Okay? Now, this atom wants 2 more electrons. That's what its goal is. It has to find 2 more electrons. Now, it can go out and steal those from somewhere. We'll come back to that one here in a bit. Or it can actually cooperate and work together with other nonmetals to accomplish this. So what you'll frequently go out and do, this is water, is what we're going to draw here, by the way. For water, what it'll do is it'll go out and find 2 hydrogen atoms, and it'll get up real close and personal with these 2 hydrogen atoms. And they'll move together so that their electron shells are actually overlapping. And then find another one. Now each hydrogen only has 1 electron because it's in group 1. Oxygen has 6 because it's in group 16. Well, in this outer energy level now, hydrogen has 2 valence electrons. One from the oxygen and the other one its own, the one that it started with. This hydrogen here has done the same thing. Meanwhile, the oxygen here, which has only 6 of its own electrons, has got 1 from this hydrogen and another 1 from this hydrogen, and it's got its octet rule satisfied. It has a full shell. The hydrogens also have a full shell because their shell, the first one, can only hold 2 electrons. So in this way, the valency requirements have been satisfied. These atoms have worked together. They have shared their electrons so that they can actually fulfill that octet rule and get all of the electrons that they need. So, a couple key points I want to mention. Electrons are shared, and there are 2 electrons required in order to form a covalent bond. This will be important when we start doing molecular structures in a couple of days. Okay, polyatomic ions, we're not going to mess with too much. Just know that they're covalently bonded. And dissolution means how easily it dissolves. The type of covalent bond that it forms, whether it's polar or nonpolar, is what really determines that. Okay, so I'll scroll down and show that actually rather than trying to quote it. So, yeah. I'm going to pull that up. I'm not going to spend a whole lot of time on polar versus nonpolar. You just need to write it down and know. So I'm going to clear this. So nonpolar covalent bond is a compound. It's actually not a compound. Hang on, that's a mistake. It is a molecule, not a compound. It is a molecule with even electron distribution. Okay, and there are only 7 elements that can form nonpolar covalent bonds, and those are the diatomics. Everything else is going to be polar to some extent. Now, there are some atoms that can fake nonpolar, like carbon dioxide, because it's linear, but we're not going to mess with that in this class. So, yeah. I'm going to assume you have that written, and that if you don't, you're going to pause it so you can get it written. Okay, cool. Now, we'll scroll over here. And once again, that should say molecule, not compound, though these are actually compounds because there's different elements. Molecule with uneven electron distribution is going to be a polar compound. This is like 99.9% of molecules. Okay, they're of covalent molecules. Okay, they are polar because the electron distribution has to do with the electronegativity of the things that are in the bond, that are forming the bond. Oxygen is going to pull a lot of electrons to it, while things like hydrogen are going to be like, yeah, take it, I don't want it, get rid of it, I don't want this. So yeah. All right, now let's go back and do ionic, and I am going to. All right, I have to do that after. I am going to pause this, or I'll step aside so you can get this written down if you didn't get it before, because you were warned. All right, now I'm going to go through this. Okay, ionic bonds are probably the most common because there's lots and lots and lots of metals, but they just kind of hang out. They don't really form bonds. We already said that. So they can't really form bonds with each other, but they can form bonds real easy with non-metals. Okay, so an ionic bond is typically a bond between a metal and a non-metal. More accurately, it's a bond between two ions, a cation and an anion. Okay, polyatomic ions can take the place of either the cation or the anion, but we're not going to mess too much with that. What happens here is something like this. So let's go with sodium chloride. Okay, so here we have a sodium atom. It's got 1 valence electron. And then just down the street a little bit, we've got a chlorine atom, which has 7 valence electrons. There we go. Okay, so sodium is desperately trying to get rid of its electron. It doesn't want this, because if it gets rid of this one, the shell underneath is already full. Okay, it's got a full shell. If it can get rid of that electron, it can satisfy its octet rule, be done. Chlorine, meanwhile, is desperately trying to find an electron. It only needs one. It's so close. But it can't find one until it comes across sodium. And what happens is this chlorine sneaks up on sodium and goes, mine, and takes it. And the sodium goes, oh darn, I'm so upset. Because it was trying to get rid of it anyway. But there is a consequence to this. When this happens, that sodium atom, now with no electrons in that shell, it's lost 1 electron. Well, when you lose a -1 charge, you become a positive ion. This now has a +1 charge. And likewise, not sodium, nope, I'll get there, chlorine. The chlorine atom now has 8. Excuse me, I changed the color. Now has 8 valence electrons. And so it now has a -1 charge because it was neutral. Here, both of them were neutral, but this one now gained a negative charge. This one lost a negative charge. Well, when you have a +1 and a -1, this is kind of like the North and the South Pole. They are attracted to each other. And that is how we get a salt molecule. These two atoms are stuck together. And this doesn't happen with just one atom of each. It happens with thousands of atoms of each. Okay, in a single grain of salt, there are hundreds of thousands, if not millions, of atoms of each of these that are laced together in a lattice pattern that we're not going to worry about in this class. Okay, because of this magnetic attraction, these bonds are incredibly strong. Okay, if you've ever stepped on a large chunk of salt, you know what I'm talking about. It's like stepping on a Lego. Okay, these are so strong, these kinds of bonds. However, they're very easy to dissolve in a polar solvent, like water. Salt will dissolve very easily in water, but trying to break the bonds, if you try to grind up a salt crystal, it's very difficult to dissolve, really easy. Okay, that's because it's a different property. That is pretty much it for this. Now we're going to go through 2 worksheets. The first one is going to be guided practice, where we're going to kind of walk you through what's going on. The second one has another 44 practice molecules for you to discern whether they are covalent or ionic. There's also a couple of metallic on there, but the main ones we want you to figure out are covalent and ionic. Okay, there is nothing with hydrogen bonds on there. You do need to know all of these things for all of the terms. Okay, so that is pretty much it. I'm going to call it there. Have a wonderful whatever, and I'll see y'all next time.